Hello and welcome to lecture number 5 in our 8th module, this online cognition series. We're going to finish up our discussions of problem solving. So previously we talked about the Gestalt approach and some research about incubation and insight. And today we're going to take a look at different types of problems and how we sort of categorize them. Then we'll take a look at problem representation and ways in which to solve different types of problems, factors that influence problem solving, and then finally we'll get to talking about some hindrances, common hindrances to problem solving. So let's get started then with talking about different types of problem. So the type of problem will often relate to the strategies and processes used to solve a particular kind of problem. Our first distinction is one I alluded to in the previous lecture, which is well-defined versus an ill-defined problem. A well-defined problem is something that has explicitly stated start conditions, goal conditions, and means of proceeding. So this is, I have a flat tire, I need to get to work. So clearly defined parameters, I got to get to work. So either I got to get the tire changed, or I have to find a different way to get to work. So pretty clear start conditions and goal conditions and means of proceeding. Certainly getting a degree has a clearly stated start condition. Start with no credits. You got to end with 120 credits. You have to have these particular courses and these particular requirements. And this particular grade average. So that's a pretty clearly well-defined problem. Ill-defined problems have no clear start, goal, or means to proceed. So how am I going to have a meaningful life? How am I going to be happy? How am I going to find my significant other? These are ill-defined problems. Even things like I want to go on vacation. Because if there's just there's no clear means to proceed. You can go anywhere. It depends on what kind of vacation you want. All of these can be difficult. One of the things you can often do is try to set some parameters in means of proceeding. So those are sort of well-defined versus ill-defined problems. To look at some ways in which we specify the more well-defined problems, we'll take a look at what's called Greeno's typology. And Greeno's typology just simply talks about different types of problems and how we might classify them. So the first is what we call a problem of arrangement. Basically, you just have to arrange things in a particular order. So something like an anagram, where we might rearrange letters to form a word, is a problem of arrangement. So this first set of letters, you can rearrange those to create the word mafia. And the second set of letters, object or object. Problems of inducing structure are ones in which we have to determine a relationship and extend the relationship. So we have to induce the structure and then extend it. And you see these all the time on Facebook, that sort of thing. Only geniuses can solve this, and then it gives you some sort of series of things, and then you have to figure out how to extrapolate what's going on in the series and go forward. So here, we have to figure out how does this series work. So we have 1, 2, 8, 3, 4, 6, 5, 6. Well, there are actually two series. There's 1, 2, 3, 4, 5, 6, and 8, 6, 4. Then it would be 7, 8, 2. So that would be how you would extrapolate that series. You have to induce the structure and then extrapolate from it. Word analogies is another one. You've taken the SAT, most of you. Some of you are going to have to take the GRE. Word analogies are a big part of that. Dog is to wolf as cat is to lion or tiger. Lawyer is to courtroom as gladiator is to Colosseum. Other things like analogous problems, and this is where we'll start to look at ways in which we can use the solution from one problem to solve another. So this is called the fortress radiation problem, and this is pretty commonly used. We have a fortress located in the center of the country. Many roads radiate out from the fortress. The general wants to capture the fortress with his army, but wants to prevent mines on the roads from destroying his army in neighboring villages. As a result, the entire army could not attack the fortress on one road, but the entire army was needed to capture the fortress. So an attack by one small group would not succeed. The general therefore divided his army into several small groups, positioned them at the small groups at the heads of different roads. They simultaneously converged on the fortress, and then this way captured the fortress. So a tumor is located in the interior of a patient's body. Doctor wants to destroy the tumor with rays. Doctor wants to prevent the rays from destroying healthy tissue. As a result, the high-intensity rays could not be applied to the tumor along one path because it would damage the tissue. However, high-intensity rays were needed to destroy the tumor, so applying one low-intensity ray would not succeed. How do we solve the problem? Well, we take the same solution as the fortress problem. So rather than sending the army along one path, we send it on a bunch of different paths. And so that's what we do. In fact, this is how the gamma knife works, is low-intensity rays are all positioned at a tumor, and you can destroy the tumor without destroying healthy tissue along the way. So the idea here is we solve by analogy. We use the solution from one problem as a solution to another. Problems of transformation are types of problems that require a sequence of operations to get from an initial state to a goal state. This is a very famous one of these kinds of problems of transformation. It's called the Hobbits and Orcs problem. Sometimes it's also called the Cannibals and Missionaries problem, but here it is. We have 3 hobbits and 3 orcs that arrive at a riverbank. They all wish to cross to the other side. Fortunately, there's a boat, but unfortunately the boat can only hold 2 creatures at a time. There is, of course, another problem. Orcs are vicious creatures, and whenever there are more orcs than hobbits on one side of the river, the orcs will immediately attack the hobbits and eat them. Consequently, you should be certain that you never leave more orcs than hobbits on any riverbank. So this requires a series of transformations. We start with all 6 creatures on one side of the river. And then, let's say we move 2 orcs to the other side. Then we'll bring 1 orc back. And then we'll send 1 hobbit over. And so you sort of have to move back and forth until you get everyone across the river safely. Actually requires a number of maneuvers. Other prior problems of transformation include the acrobats problem, which is very similar to the Tower of Hanoi or the Tower of London. So here we have the acrobats. We start off in this initial state. We want to move everyone over to this state. Obviously, a larger acrobat cannot be on top of a smaller acrobat. So we might have this guy jump here, and then this guy jump over here, and then this guy can jump on his shoulders. I don't know, something like that. So you sort of work your way through that to get to this goal state. Very similar is the Tower of Hanoi or the Tower of London, where you start with these 3 discs, and you move 1 disc at a time, and you can only move a disc when there's no disc above it, and a larger disc can never be put on top of a smaller disc. And so we are transforming this into a different way. So you can actually go to some, there's apps available for your phone if you want to try this out, if you're kind of bored. But it's an interesting way to see how these kind of transformation problems work. We actually saw this problem earlier when we talked about patient HM and his ability to learn this problem with no memory of having done so. So that gets us in at different methods for solving problems. The first of these is comparing heuristics to algorithms. Algorithms are a series of rules or steps that guarantee a solution if followed correctly. Heuristics are shortcuts or rules of thumb. And in fact, a lot of problems are solved very easily through these kind of shortcuts or rules of thumb. One of the problems with a complex game like chess is algorithms are too slow and clunky for competing in a chess competition. And so heuristics are when an expert can look at the board and know the positions of the pieces and know exactly what move they should make based on the position of the pieces without having to go through an entire set of algorithms. So heuristics are often a more effective way to go. And we'll talk more about heuristics and decision making in the next series of lectures on decision making. So some common heuristics for problem solving include means-end analysis, where we simply determine the difference between our current state and our goal state. And we do this all the time. I want to save $10,000 to go on an elaborate vacation, really just a normal vacation, day at Disney World. So, you've got $100 in the bank. Now I've got $9,900 to go. And so we're just constantly comparing where we are to where we want to be. Same with your college degree. Where am I now? How far have I got to go? This is commonly used in transformation problems It is, however, not always the best strategy. So, for example, in the Hobbits and Orcs problem, you have to move away from the goal in order to get to the goal. In fact, that's the fastest strategy. Another thing is to establish sub-goals. I think this is great, particularly for a big, complex problem. Like your undergraduate degree, I want to get my gen ed out of the way, I want to get my major requirements out of the way, my minor requirements out of the way, and then, etc. So these are states that are intermediate to the goal state. In the Hobbits and Orcs problem, the most effective is to reach a sub-goal of 3 orcs across the river. You can actually save about 10 moves doing it that way. So sub-goals are a really good way to go about anything that's going to require a particularly lengthy amount of work. Solution by analogy, again using the solution of one problem to solve another, like we saw in the radiation fortress problem. If you're planning on going to law school and taking the law school admissions test, one of the things I highly recommend is practicing the logic game section to death, because there's a pattern to those, and so when you get into the actual LSAT, you'll have solved almost all of the different types of problems at least once, or hopefully several times, and you can use the way you did it for a different problem to solve those problems. So that gets us then to factors that influence problem solving. One of them is, of course, what the strategy you might use to try to solve the problem, so means versus means end, sub-goals. The next is particularly important for a number of different types of problem, is the way in which you represent the problem. And so there's a really terrific set of studies by Kaplan and Simon using what's called the mutilated checkerboard. So you're given a checkerboard and 32 dominoes. Each domino covers exactly 2 adjacent squares on the board, plus the 32 dominoes can cover all 64 squares of the checkerboard. Now, suppose 2 squares are cut off at diagonally opposite corners of the board, like this. Is it possible to place 31 dominoes on the board so that all of the 62 remaining squares are covered? So in my in-person classes, I actually hand out a photocopied version of a checkerboard and break students into groups to see if they can solve this. So here's the problem. Can we use one less domino to cover this entire checkerboard? Well, Kaplan and Simon did several different versions of these. There's a blank version, the color version, and then different words, so pink and black and bread and butter. And they discovered that participants were more likely to solve this problem depending on how it was presented. In particular, I believe the boards with words on them were the most efficient, and the blank was the least efficient. And certainly the blank doesn't allow you to represent the problem in the way that you might with this kind of solution. So the answer to this problem is that no, you cannot use one fewer domino, and the reason is that one domino, let's go back, you can see will cover a black square and a red square. Because we've cut off diagonally opposite corners, we've taken out 2 red squares. Because a domino has to cover a black square and a red square, no matter how you slice it without cutting the domino in half, there's no way to do it with one less domino, because we've taken away 2 red squares. We would have had to take away a red square and a black square in order for that to work. And so it's that simple. And one of the reasons why there's differences here is because you can say, oh, well, we've taken out 2 squares that say butter, which means each domino is covering a bread and a butter on the side, for example. So that's the mutilated checkerboard problem. Another good way to represent problems is using symbols. So Mary is 10 years younger than twice Susan's age. 5 years from now, Mary will be 8 years older than Susan's age at that time. How old are Mary and Susan? And we just plug all this into a formula, and we end up solving it this way. So Mary is 10 years younger than twice Susan's age, so x equals 2y minus 10, right? So then we can solve for x, and we can solve for y, and then substitute everything out. Matrices, those of you, again, who are thinking about taking the LSAT, this is a kind of problem that you're going to get quite a bit of. 3 married couples, the Rubin, the Sanchez, and the Taylors, have a rather unusual thing in common. All 6 3 husbands and 3 wives are psychiatrists. Their names are Karen, Laura, Mary, Norman, Omar, and Peter. As fate would have it, each doctor has one of the other doctors as a patient, but not his or her own spouse. Several other key facts are, first of all, these are all heterosexual couples. Karen is a psychiatrist for one Dr. Rubin. Laura is a psychiatrist for the other. That means that Mary is Dr. Rubin. Mary is the patient for one Dr. Taylor. Peter is the patient for the other. Laura is a patient of Dr. Sanchez. And Peter has his psychotherapy with Omar. Determine everyone's full name. Well, you can actually use a matrix like this and figure out, so for example, we know Karen and Laura are not Dr. Rubin, so we would X out Karen and Laura under Dr. Rubin, which means that Mary has to be Dr. Rubin. Well, we know Mary is not Dr. Taylor, so we don't need to even worry about that. So Peter is not Dr. Taylor. Laura is the patient of Dr. Sanchez. So that means she's Laura Taylor and Karen is Dr. Sanchez, etc. So you can go through and kind of mark these out. Many of these logic problems are similar to Sudoku. Basically, it's an inferential structure where you have to try to eliminate possibilities and figure out a solution. Another great way to solve some of these problems is to use a diagram or a graph. This is one of my favorites, the Buddhist monk problem. So exactly at sunrise one morning, a Buddhist monk set out to climb a tall mountain. The narrow path was not more than a foot or two wide, and it wound around the mountain to a beautiful glittering temple at the mountain peak. The monk climbed the path at varying rates of speed. He stopped many times along the way to rest and to eat the fruit he carried with him. He reached the temple just before sunset. At the temple he fasted and meditated for several days. Then he began his journey back along the same path, starting at sunrise and walking as before at variable speeds with many stops along the way. However, his average speed going down the hill was greater than his average climbing speed. Prove that there must be a spot along the path the monk will pass on both trips at exactly the same time of day. Now, if you want to take a moment to try to solve this, you should pause this because I'm going to move on to show you the solution. If you want to take a minute to try to solve this yourself, I recommend doing that. So, spoiler alert, here we go. What you do is you create a graph. So you can see we leave at 6 a.m. The monk leaves at 6 a.m. on his way up, wanders his way up the hill until he gets to the top of the mountain peak at 2,000 feet. Then when he heads back down at 6 a.m., he comes back down, and these two lines have to cross at some point, given all the parameters of the solution. And it doesn't matter how you graph this out, at some point these two lines have to intersect. So there has to be a spot at which he crosses at the same time on both journeys. Other factors that influence problem solving include characteristics of the information processing system. In particular, working memory capacity is an important part of problem solving, and ability to retrieve information from long-term memory. So we know individuals with greater working memory capacity have higher fluid intelligence, and high-pressure situations may reduce performance in those with high working memory capacity. So problem solving may become problematic in those who are in high-pressure situations or under a great deal of stress. So it's always something to keep in mind. Other issues are things like task environment. How is the problem represented? So there's what we call the reverse acrobat problem. And of course the mutilated checkerboard problem. Oftentimes giving people the checkerboard itself inhibits their trying to solve the problem. And then finally, prior knowledge. Can you transfer the solution from one previously used solution to another? So that gets us to the last topic to discuss here, which is common hindrances to problem solving. Mental set is the tendency to use the same solution over and over again, and this is demonstrated pretty clearly by what's called Luchen's water jug problem. And without spending too much time on this, essentially what you do is you give, the idea is participants have to come up with this desired quantity. So we need 100 units. So, and we start with these three jug sizes. So jug B, we have 127 units. We pour out 1A, which gets us to 106. We pour out C, and pour out C again, we end up with 100. So it's B minus A minus 2C. Now, all of these can be solved using B minus A minus 2C, and the first several of them can only be solved that way. But if you get down here to number 8, there's a much easier solution, A minus C. But participants tend to still use B minus A minus 2C because they have gotten a mental set. And this is one of those things that happens to us all the time. We keep trying to use the same solution over and over again. We'll restart our browser or our Wi-Fi over and over again. As many times, I'll restart my Wi-Fi and my cable box for hours before I think to call the cable company and see what's wrong. Because we use that same solution over and over again, and eventually it usually works. So that's one of those problems. So it's this bias or tendency to solve problems in one particular way. So we get a mental set, this is how we solve this, when in fact there might be a better or easier solution. Finally, functional fixedness. This is the candle problem. This used to be more effective before the DIY era. But essentially here's the problem. You're supposed to use these materials to hang the candle on the wall. Most people think that the matches are there simply to light the candle. However, if you dump the matches out of the box and tack it to the wall, you can stick that candle right in that box. So it's a pretty easy solution once you figure that out. So only about 39% of subjects could solve that problem in 10 minutes when that was originally proposed. Then there's the two-string problem. They're given a scenario like this, and even in some cases are actually put in a room that's built like this, where you can't reach both strings, but your task is to tie those two strings together. And there's actually a pretty direct solution, and we will now show you my favorite animation ever. So by attaching an object to the string, she's able to use it as a pendulum, and then get a hold of the other string and tie them together. The problem is, with functional fixedness, it's our tendency to use an object only in its customary or usual way. So we are fixated on that particular function, and so we don't think about using something in a different way. So these are some of the common hindrances to problem solving. In our next lecture, we're going to talk about choice models and normative decision making.